Hey everyone, and welcome. If you're getting ready for your CSEC chemistry exam, you know some topics are just, well, they're the foundation for everything else. Today, we're going to jump into one of the big ones, atomic structure. Let's get right into it.
Have you ever just stopped for a second and wondered, what is everything actually made of? I mean, what are the fundamental ingredients for, the chair you're sitting on, the air you're breathing, or even you?
Well, the answer is actually pretty simple. It's all about atoms. Think of them as these super, super tiny building blocks that construct our entire universe. And today, we're going to get to know them, inside and out.
So, here's what we've got on tap. First, we'll get a handle on why atoms are the building blocks of everything. Then, we're going to peek inside and meet the tiny particles that live there. After that, we'll learn how to read their special identity cards, check out their atomic twins known as isotopes, see some of their amazing real-world uses, and finally, we'll put what you've learned to the test with some exam practice.
Okay, so let's lock in that main idea. Atoms are basically the Lego bricks of the universe. Every single element you can think of, from the hydrogen in water to the gold in jewelry, is just made of a different type of atom. But what are those Lego bricks made of? What's inside an atom? Let's zoom way, way in. For your CSEC exam, you really need to get to know the three basic or subatomic particles that make up pretty much every atom.
All right, first up, the proton. A really easy way to remember this one is P for proton and P for positive. These guys are kind of the heavyweights, and they all hang out together right in the center of the atom, in a dense little core we call the nucleus. And living right there in the nucleus with the protons is their roommate, the neutron. Again, super easy, and for neutron and for neutral, it has no charge at all. It's about the same size as a proton, so you've got these two packed together, making that nucleus super dense. And finally, whizzing around the outside of that nucleus, you've got the electrons. These little guys are negatively charged, and they are incredibly light. Now, for CSEC chemistry, you don't have to get too complicated here. Just picture them moving in these fixed paths, kind of like planets orbiting the sun. We call these paths shells.
Okay, this table right here, this is gold for your exam. Let's walk through it. So you can see the charges are pretty straightforward. Proton is +1, electron is -1, and the neutron, 0, zip, nada. Now look at the mass. We just say protons and neutrons each have a relative mass of 1, but look at the electron's mass. It's so incredibly tiny, it's almost nothing in comparison. Seriously, getting this table down will save you a ton of headaches.
So hold on a second. If everything's made of just these three little particles, how do we get all the different stuff in the universe, like carbon and gold and oxygen? Well, it turns out every atom has its own unique identity card, and it's all about the numbers. And the single most important number, the one you absolutely have to know, is the atomic number. This is literally the atom's fingerprint. It's just the number of protons it has. If an atom has 6 protons, it is carbon, period. If it has 8 protons, it is oxygen. No exceptions. That's the rule that defines what element it is.
Okay, next up is the mass number, and it's pretty much what it sounds like. It tells us the mass of the atom's nucleus, where all the heavy particles are. To figure it out, you just add up the protons and the neutrons. Simple as that.
So how do chemists write all this down without, writing a whole paragraph? They use this shorthand. Let's just use X to represent the symbol for any element. You'll always see 2 numbers with it. The one on top, A, is your mass number, and the one on the bottom, B, is the all-important atomic number. Okay, so how do we actually read this thing? It's super easy. Just remember, the bottom number is the number of protons. The top number is the protons plus the neutrons. So if you need to find just the neutrons, you just do a little subtraction. Top number minus bottom number. Done.
Okay, you think you've got it? Let's do a quick check. Here's a sodium atom. Using that little rule we just learned, how many neutrons does it have? Go ahead and pause here if you need a second to figure it out.
So how'd you do? You just take that mass number, 23, subtract the atomic number, 11, and you get 12. So a sodium atom has 12 neutrons. If you got that, you're on the right track. Awesome. All right, let's move on to something that can seem a little tricky at first, but I promise it's not so bad. We know the number of protons is what makes an element, well, that element. But what happens if we change the number of neutrons? When that happens, we get these things called isotopes. You can think of them as atomic twins.
Now, this is the official definition you'll want to have locked in for your exam. Isotopes are atoms of the same element, so they have to have the same number of protons, but they have a different number of neutrons. This means they act the same in chemical reactions, but one is a little bit heavier than the other.
The go-to example for this, and you'll see this one a lot, is carbon. On one side, you've got your standard carbon-12. It's got 6 protons and 6 neutrons, giving it a mass number of 12. On the other side is its famous twin, carbon-14. Notice it still has 6 protons. It has to, or it wouldn't be carbon anymore, right? But check out the neutrons. It's got 8 of them, making it just a little bit heavier. Okay, so what? Why are these isotopes even important?
Well, some of them, like that carbon-14 we just met, are a little unstable or radioactive. And yeah, radioactive can sound a bit scary, but it turns out scientists have figured out some incredible ways to use these isotopes to help people.
For your exam, you should probably know a few of these uses. First, there's carbon dating. That's how scientists can tell how old ancient things, like fossils, actually are. Then in medicine, you've got things like radiotherapy, which uses the energy from radioactive isotopes to target and zap cancer cells. And doctors can even use them as tracers to watch things like blood flow inside your body without ever having to do surgery. Pretty amazing stuff, right?
Okay, we have covered a ton of ground, so let's put it all together and see what a typical CSEC exam question on this topic might look like.
All right, let's break this down together. First up, protons. This should be the easy one by now, right? The atomic number is 9, so that means we have 9 protons. Easy. Next, the neutrons. How do we find them again? Oh yeah, mass number minus atomic number. So that's 19 minus 9, which gives us 10 neutrons. And finally, the electrons. Now pay attention to the key word here, neutral. Neutral means the positive charges and negative charges have to cancel out. So if we have 9 positive protons, we must have, you guessed it, 9 negative electrons to balance it out. See? You've got this. So there you have it. We've basically built an atom from the inside out. But let me leave you with a little something to think about. All those protons are positively charged. And you know how positive charges are supposed to push each other away, right? Like when you try to force 2 magnets together the wrong way? So what kind of mind-blowing superglue is holding all those protons together in that tiny, tiny nucleus? Well, that's a story for another day. It's called the strong nuclear force, and it's a huge deal in physics. But for now, you've mastered the atom. Thanks for joining me.